Welcome back to physics. So, what we got planned for today is we're going to keep talking about waves, but we're going to be talking about a different type of wave, and that is sound waves. Okay, this is probably one of my favorite topics to cover in physics, along with energy and momentum and pretty much everything else. Okay, but this one holds a special place in my heart because, as you guys know, not only am I a very big physics nerd, well, at least some of you might know, not only am I a big physics nerd, I'm also a big math nerd, and also a big video game nerd. I'm also a big music nerd. I love listening to music, and I love talking about the physics of it. Okay, so that's what we're going to be doing today. So, before we talk about sound waves, we have to talk about what is sound. Now, sound is just wiggly air. That's my favorite definition of it. But really, what it is that it's a wave made up of compressed and decompressed air molecules or particles in the air. Okay. So what I'm doing when I'm talking to you is I'm compressing air in front of my face, and then it wiggles, right? And then I don't know why I'm saying that, but it sends a signal to you guys. Again, it's transferring energy and it's transferring information. Okay, so just like waves on a string, or a mechanical wave, sound also needs a medium to travel through. Usually, sound's always going to travel through air. That's how we normally hear of sound, right? And basically, everything that we've ever heard is just complex, just different complex patterns of wiggly air, and that's it. Isn't that really weird to think of? Okay. And also, it's a longitudinal wave, showing that, which means that the disturbance is in the direction of the wave. So right now, I'm disturbing the air, making it wiggle back and forth in front of my mouth, and then the wave is going to travel towards you in the direction of that disturbance. Okay, so if we were to get a more accurate representation, so this is why I'm sort of filming in my office. I'm going to be doing a lot with computers and also a quick demonstration on my guitar. I just figured that I'd give my camera woman a break and film in my office. The thing is, we only have one lamp in here, so I sort of repurposed this book light or reading light or whatever. So that's what's going on right now. But anyways, here's a pretty good. Can I change the? I don't know if I can change the. I can't change the camera angle, so I'm just gonna have to point you towards the screen and hope that I'm showing you what I want to. Okay, but this is a more accurate representation of a sound wave. If you notice, we see that the crests of the wave, we can follow them along as it travels. Now, they're made up of just the more compressed sections of air. And the troughs are sort of the sections in between those crests. That's when the air is the least compressed. The fancy word for that is rarefact, but I don't like to really use that. So again, the wavelength is going to be the distance between those two crests right here. Now, if you remember, the frequency of a wave is how many cycles it does every second. Okay. See, are we still pointed towards it? We are. Okay. Okay. But the frequency is how many cycles per second is the wave, I don't know, cycling. So it's how many compressions of air hit your eardrum every second. All right. So when we, but really what the frequency of a sound wave is really the pitch, right? We've heard of pitch before, right? So a high pitch is a high frequency. Low pitch is a low frequency. Okay. Also, the amplitude of this wave is really just how compressed those little air molecules are. If they're really tightly compressed, we have a high amplitude, which also means a very loud sound. The less compressed they are, it's going to be a low amplitude, therefore a low sound. All right, and then the last thing I want to talk about right here is, again, if you look very closely at the dots in here, there's actually some colored red, okay? But if you follow them, you see that they're not moving with the wave. Every single one of these dots is just moving back and forth, right? So this is an example of how waves do not transfer mass. These little particles are just staying relatively in the same place, but just making very slight movements, like so. Okay. All right. Moving on. Oops. All right, there we go. All right. So, next, when talking about sound and the frequency of sound, I want to mention this little thing called the Doppler effect. Now, the Doppler effect is great, and whether you know it or not, you have experienced the Doppler effect before. If you've ever walked along a busy street, you've experienced the Doppler effect. Okay, so basically what that is when a car passes you, you hear that sound. Or especially if they're honking their horn, you definitely hear that. Okay. There's no other way that I could describe it other than that. Okay. But now, let me give you sort of a visual representation of how am I going to do this? I think this is the screenshot button. Okay, I don't know if I can. All right, well, we're going to give this a shot. Okay, so what I have here is just a piece of paper with a bunch of tick marks on it. Okay, now this large paper clip is going to be our car. Okay, and our car is going to travel 1 tick mark per second. Now that car is also honking its horn, so it's going to be emitting sound waves. And we're going to make it so that the sound waves travel 2 tick marks per second. Okay. So, boom, 1 second has passed. It's going to emit these 2 sound waves. They're going to travel 1, 2 tick marks away. And then in that time, boom, the car moves over 1 tick mark. All right. 2 seconds pass. These 2 have moved over 2, and then we have 2 new sound waves like this that are again 2 tick marks that have traveled 2 tick marks away from the source, and then we're going to move the car again. Another second has passed. These 2 paper clips again move ahead 2 spaces, 2 tick marks. So do these. Oop, I lost my place. I think they're right. No. Should be like here-ish. Okay. And then we have another sound wave over here and another sound wave over here. All right, they're both 2 spaces away from this source. And again, the car moves 1 tick mark. Now what we see here is a bunching up of sound waves in the direction that the car is facing, and then a separation of the sound waves in the direction that the car, in the opposite direction that the car is moving. So if you're on this side, if you're on this side of the car, you experience those 3 sound waves at a much greater frequency. You hear it like boom, boom, boom. Right? Higher frequency means you're hearing a higher pitch, the nee. Okay? Now, as the car passes you, you're going to be on this side of the car, where the sound waves are spaced out farther, which means that we have a lower frequency, like a kind of deal. So that's the part of the Doppler effect. Okay, so this is what happens. So when the car moves towards you, the sound waves bunch up together, resulting in a higher frequency and a higher pitch. And when it's moving away, the sound waves space out, and we hear a lower frequency with a lower pitch. Alrighty. Ooh, sorry I had to see that, man. No, sometimes lighting does you wonders, and then other times it just doesn't work out. Okay, so, I forgot to pull this up. So I have I have a video to show you guys. It's probably one of my favorite, if not my favorite, demonstrations of the Doppler effect. It's this Scotsman with a pair of bagpipes going bungee jumping. And you'll see that. Oh, here we go.
Piper. Ready for this?
Okay.
Cracking chocolate tea. Yeah.
There's this crazy Scotsman, and he's got some bagpipes. So, if you, I hope you heard it, but while the, let's play it back actually. While the Scotsman was falling, we heard that lower frequency, that lower pitch, and as he rises up, we hear the pitch getting higher and higher. So he goes low, and then high. There we go. I hope you were able to see that. I wish I could sort of change the little perspective on the fly, but I guess not. I guess that's just proving my boomerness now. I'm getting old. Anyways, so that's the Doppler effect. It's really fun. Now, it wouldn't be a physics lecture without a little bit of spicy math, okay? So on the next slide, we have a little equation for the Doppler effect. Where we have all of these new symbols. So F is still frequency, but now we have 2 different frequencies. We have F prime, which is the F with the little apostrophe next to it. That's going to be the frequency that you yourself hear. That's the frequency that you observe. Okay, now F is the actual frequency of the source of sound, for instance, the bagpipes, right? So, to the Scotsman, as he's falling, those pipes stay the same pitch the entire time because he's moving with those bagpipes, okay? It's sort of like an auditory illusion. You hear a different frequency, but the actual frequency stays the same. So that's what F is. Next we have V, just by itself. That's the velocity of sound. That's the speed of sound in air. It's about 343 meters per second. That's pretty much going to stay the same for every every problem that we do. Okay, so VO is the velocity of the observer. VS is the velocity of the source, where the sound is coming from. So, I don't know how we're going to do this, but we're going to do an example. Okay. So, we have an insane Scotsman riding towards you on his unicycle at a speed of 10 meters per second. That's pretty impressive for a unicycle. That's about 20 miles per hour, a little bit more or less. Can't remember. His bagpipes are droning, and I actually tried to find the pitch that's going on here. The bagpipes are droning with a frequency of 117 hertz. What is the frequency that you hear? So it's giving you F. We're trying to find F prime. How am I going to do this? I don't know. There's some technical... Well, we're already 16 minutes in. We're going to roll with it, okay? So, first of all, I'm just going to start out by writing the givens. It says an insane Scotsman is riding towards you at a speed of 10 meters per second. So, that's going to be Vs, the velocity of the source, is equal to 10 meters per second. His bagpipes are droning at a frequency of 117 hertz. That's going to be regular F, 117, right? So some other givens that we know but aren't said in the problem is one, V by itself is just the speed of sound, 343 meters per second. You know what? Okay. I'm gonna put the solutions to this problem in the PowerPoint. That's what I'm gonna do. And if I don't have it in there, please yell at me, because I want you guys to learn. That's what I'm gonna do. All right. V is equal to 343, and the velocity of u. So it's assuming that you are just sort of standing there at rest. You have a velocity. The velocity of the observer is equal to 0 meters per second. All right, so that's all of the givens in the problem. Now I'm just going to rewrite the equation. F prime is equal to V plus VO divided by V minus VS. And I know that some of you are thinking, like, hold on. Actually, no, we'll do that the next problem. Okay. So F prime is what we're looking for. It's already by itself. We don't have to change it at all. That's going to stay the same. We're going to plug in V, which is 343, plus the velocity of the observer, that's 0, divided by 343 minus the velocity of the source, minus 10. And we take that whole fraction and then multiply it by 117. Okay, so make sure when you're typing this in the calculator, when you have two things being added together and it's in a fraction, you have to make sure you surround it in parentheses, or else you're not going to get the right answer. So so it's a set of parentheses, and then a set of parentheses here divided by more parentheses, just to be as safe as possible. Okay. So we're going to take 343, divide it by, in parentheses, 343 minus 10. Okay, and then we multiply that by 117 hertz. We get a new frequency. I'm pulling out the expo marker. I don't need this. Is equal to 120.5 hertz, roughly, right? Okay. There's the work I have. Can you read it? It looks like no, unless they're gonna flip it on me. All right. Now we have another problem just below that. So let's say that not just The Scotsman on the unicycle is moving, but you are also moving as well. You're going to be moving towards him. So like this. So you're going to be moving at 20 meters per second. Scotsman is going to be moving at 10 meters per second. Okay. And now, I know what some of you may be thinking, right? We're talking velocity. Velocity has direction. That means one of these has to be negative. Okay. But you're in luck. When these equations were created, they already had that in mind. So this is a big brain equation. So it's already actually factored into the equation so that you don't have to worry about which one's positive, which one's negative. You just put the number in. Okay. That's what's great about this one. I like this. Okay, so the givens are going to be the same, except for one little thing. The velocity observer, u, VO, is going to be 10 meters per second. Okay, so we're just going to plug in all of our numbers again. V is still 343. It will always be that, unless we're talking about sound traveling through something other than air, which we won't. Plus 10, all right, because that's the velocity of the observer, divided by that same 343 minus 10. Okay. This whole thing multiplied by 117. So, parentheses, double parentheses actually, right? Because we have the 343 plus 10, have that in parentheses, divide by, in parentheses, 343 minus 10. Oops, hold on a second. The first one is plus 20, not plus 10. Little whoopsie. Alright, so we have 343 plus 10 divided by 343 minus 10. Okay, and we take that whole thing and multiply it by the original frequency, 117. And now we get a frequency of about 127.5 hertz. Okay, so we see that because not only is the Scotsman moving towards you, you are moving towards the Scotsman. So it's sort of like when you're on the highway and the cars passing you look like they're going a lot faster than they normally are, right? That's because of the relative velocity of both of you. Okay. All right. So I will have this work on the PowerPoint, and again, if I don't, yell at me. All right. All right. Well, that's probably the hardest part of this lecture. We have a few more slides to go. So I was thinking this was going to be a long lecture. Maybe it's not going to be too long. Okay. So next. So we already established that sound is waves. Sound is a wave. Okay, so just like waves, especially like the ones on slinkies and strings like we did yesterday, sound waves can also interfere with each other. So when peaks meet peaks, right, so the peak of one wave meets the peak of another wave, they add together to get a higher peak. That's a constructive interference. That means it's going to result in a louder sound, a larger amplitude, so louder sound. Okay. Next. So, that also happens when troughs meet troughs. Okay. A low point in a wave and a low point in a wave meet each other, and then they add together to create an even lower point in the wave, right? And just because it's negative doesn't mean it's soft. It's still far away from that zero line. That also results in a loud sound. Now, when a peak meets a trough, they add together and cancel out. That's going to result in a quiet sound. So when you play two different frequencies at the same time, right, they're not always going to line up with each other. It's sort of like the hands on a clock. Those move at different frequencies, right? Right? So when they line up, right, that's going to be constructive interference, but then they're going to cross paths and they're not going to be together anymore, right? So, only at select times do they actually line up. All right, I have a little diagram on the next page that shows you that. So you'd think that just looking at these two waves, they seem very similar to each other, but they're actually not. They're actually about 3 hertz off. So I don't know. I can't be bothered to count the waves. Let's say that one is about 50 hertz and the other is about 53. Okay. They're actually 3 hertz apart. So when you play these two frequencies together, you actually get something called a beat frequency. All right. So a beat frequency is a frequency that results that you get when you add two frequencies together. So once you overlay those two frequencies together, you'll see that at some points there's going to be constructive interference, and at some point there's going to be destructive interference. Okay, so the beat frequency, this is a very simple equation, is just the frequency of the first one minus the frequency of the second one, and then you put that into absolute value lines. Okay, so for example here, if we have a 53 frequency, a 53 hertz wave and a 50 hertz wave, you play them at the same time, you get a 3 hertz beat frequency. Okay, so let me show you an example of what one of those would sound like. So right here, what I have is a little tone generator. It just generates sine wave tones, and it's kind of annoying, but it's also pretty cool. So what I have is actually two of these open. I have 2 tabs open of the same thing. You can just Google tone generator. You can play around with it, however you want. Okay. So what I'm going to do, so we have 2 frequencies of 440 hertz. That's A4 for you music people out there. By the way, if you're a music person, you're gonna this is a great lesson. I love it. Okay, so I'm going to change one of them to about 444 hertz and leave the other one at about 440. So I'm going to play 440. Now I'm going to play 444. Okay, so unless you have insanely perfect pitch, you won't be able to find to tell the difference between those two frequencies, right? So that's why it's sometimes hard to tune by ear just by hearing one tone. Okay, but now if we play those 2 tones together, we get something different. So I'm going to play the 444 and then the 440. Now that is the beat frequency. So I know that maybe when I was trying to explain it, I didn't do the best job. Alright, it's just something kind of hard to explain until you actually hear it for yourself, okay? So again, we have 444 hertz and 440 hertz, okay? So subtract those two, that's a beat frequency of 4 hertz. So we hear 4 sort of flashes, for lack of a better term, 4 pulses of sound every second. Okay, so let's listen to it again. Okay, so yeah, that's example of a beat frequency. And it's actually a really helpful term. It's a really helpful tool, that's the word I was looking for, tool, to help you tune your instruments, right? Do I have this tuned already? Tuned enough. Alright. So what I have is this guitar right here. This is my Taylor GS Mini. Bought a few years ago. It's the only nice guitar I have. I love it. Been using it ever since. And I'm gonna bust it out in the next few days, once we get to light. Alright? But for now, so for those of you familiar with guitars, I'm not, well, first of all, I want to say that I'm not good at tuning at all. I don't have a good ear for tuning. But what you can do is we have the E string right here. It's the very bottom string. And then right above it is the B string. Now, when you put your finger on the 5th fret of the B string, you get the same note as the E string. Same note, but different strings. Okay, so now what I'm going to do is I'm going to actually detune the guitar. So once the frequencies start getting farther and farther away from each other, you'll start to hear the beat frequencies sort of speed up. Okay, we're 30 minutes in, so maybe this isn't a short one. All right, let's go. We're pretty much towards the end. All right, so I'm going to play those two notes at the same time and then change the tune of the E string. Hear those beat frequencies? All right. So if you're a musician, probably a string musician, but I don't know. Maybe this works with woodwinds and stuff like that. I wouldn't know, but and I also wasn't in band. But give it a shot, I guess. If you have another friend, have them play something and compare the beat frequencies. Maybe that's how they do it. I don't know. All right, so now we have a horribly detuned guitar. At least the bottom string, okay? So I'm going to try and fix that. So I'm going to get it so that the beat frequencies slow down as much as possible. Right? We try to get that difference between the two frequencies to be very small. So let's give that a shot. Am I doing this wrong? I am. That's better. Still hear the beat frequencies. Okay, now I just tuned it too high. So if you might have heard that the beat frequencies actually sped up a bit. So that means I sort of passed it and I need to go back. Good enough. Alrighty. What do we have next? Ah, yes, okay. Physics of harmony. So, this is again for some of you music nerds like me, some of you band kids, some of you orchestra kids, some of you choir kids. This is pretty much optional, so you can leave if you want to. Goodbye, I'll see you tomorrow. But if you want to stick around, I got some really cool stuff about harmony. Well, it's still cool, but it's pretty short. Okay. Alright. So, how am I gonna film this? I don't know. I hate this. I should have switched it up. Alright. But I want to talk a little bit about harmony, otherwise known as notes sounding good together. Okay, so two notes that in my opinion and in a lot of people's opinion sound good together are G and D. put them together, you get a G5 chord. And they're the basis to a wonderful G major chord. Alright, so what I'm going to do is then look at this little tone generator again. So a G note, let's say G2, it sounds like this. Oops. That's my subwoofer right there. Doesn't that sound great? Okay. And then we have the D note. It's bassy. Alright. So that's actually, despite how distorted my speakers make it sound, that's actually a very nice interval, more commonly known as the major fifth. See, look at that. I know some music. And when you subtract those two numbers, you get a beat frequency of, I don't know, let's see. So G2 is 98 hertz, minus D2, which is about 73 hertz, okay? The difference between those two is 25 hertz, so we get a beat frequency of 25 hertz. So now we actually have three frequencies playing around with each other. Wait, hold on a second. Okay, we're actually going to do this with G3 and D3. So G3 is 196 and D3 is 147. So we're going to take 196 minus 147. We get 49 hertz, which actually turns out to be, oh, G1. There we go. Okay. So now again we have three different little what's the word? Frequencies playing around with each other at the same time. Okay. So we have 196, we have 147, and we have 49. Right? So now we have a beat frequency between 196 and 49. 196 minus 49 is 147. That's already a frequency that we have, right? So this is very, very simple. Not a lot of overtones, not a lot of beat frequencies going on. All right, this is an example of consonance, which means notes sounding good together. All right, now if we do a little bit more of a complicated interval. Oh, okay, and then we also have 147, which is D3. And again, subtracting that 49, we get 98, which is also a G. That's G2. Okay, so all of these notes are playing very nice together because it's a perfect fifth. But the reason why is because when you subtract those, all of the beat frequencies also play very nice with each other. Okay, now if we take a more dissonant interval, say the tritone, my favorite interval, that's going to be a G to about a C sharp. So it sounds like this. Wait, hold on. A G to a C sharp. G, I'm going to turn it down a bit. The best interval, okay. So this is fun fact. I think this was also known as the devil's interval back in the old days, because when a lot of music was only being created by the Catholic Church, they thought that this interval would summon the devil, which I think is very interesting, and it's actually an interval that Black Sabbath would play in one of their first songs, which is interesting. But anyways, so now we're going to a G3, which is 196 hertz, and to a C sharp 3, which is about 139 hertz. Okay, so subtract those two, we get a beat frequency of 57. 57 hertz is in between an A and an A sharp. So already it's like, it's dissonant because it's giving you an overtone that's not actually a note. So now we have 3 frequencies going on right now. We're going to do 196. Let's see, sorry. We're going to do 139 minus our beat frequency, 57. That gives us a frequency of 82. That turns out to be an E, which, I don't know. And now we have an 82 and a 57. That gives another beat frequency of 25. So it gets messy because you keep getting more frequencies, and those more frequencies add together with each other, getting a very big mess. And so you get a harmony that sounds really gross. Like this. Actually, it doesn't sound that bad. It doesn't sound that bad. I think it actually looks pretty cool. But that's the subjectivity of music. Alright. Alright, this sounds good to some people. This sounds good to some people. I don't know. That's why I like music so much. But anyways, that's the physics of harmony. I'll have that little tone chart put up into the PowerPoint as well. So anyways, thank you guys for sticking around, seeing the little bonus part, watching me nerd out about music. I hope you did too. Anyways, I'll see you guys tomorrow where we have another lecture, and then we're going to have a worksheet on Friday. So stay tuned for that. Anyways, have a good day, and I'll see you later. Goodbye.